Professor Smith this year in person, and I met him online about a year ago. But I heard about his work since I joined the EPA when I was a postdoc. So today I'm going to talk a little bit about how in silico approaches can be used in combination with the key characteristics. And there's a lot to cover, and there are so many different ways. But what I wanna suggest today is how to use the in silico approaches to maybe try to understand a little bit what's going on with underneath these key characteristics and touch a little bit on the key features. And this is something also Professor Rife earlier mentioned a little bit. So in silico approaches in general are used a lot to do screening work. So mainly make predictions and replace the long processes and the costly processes of screening traditionally a lot of chemicals. So this is has a lot to do with many chemicals instead of one chemical at a time. And I want to change the thoughts that are being circulating around that in silico approaches are always like a black box, and you just get data in and get predictions out, and then you take that prediction and then you do something else with it. I want to say that in silico approaches and QSARs in general, they can be used also to understand the mechanistics and what's going on and what are the key features that are participating in for a specific endpoint. And here I want to mention the conceptual basis of QSARs and QSPRs, which is the congenicity principle, which means similar chemicals are associated with similar biological activity, or here, if we want to talk about toxicity. And the main issue is, what is similarity? This is a big question. So I want to take this opportunity to mention that we're going to have a workshop in October to talk a little bit and cover similarity at the NTP. And you're all invited. It's going to be a virtual event. But similarity is very hard to define, and it depends on what kind of similarity you want and what's the endpoint, what's the goal, what are you trying to accomplish. Is it like for these shapes here, is it the shape, the color, the size, the pattern? All these here are similar, but what's your goal that defines the similarity? And it's the same thing with the key features behind the key characteristics. It depends really on the key characteristic that you're studying that determines which key features are most important. And here I'm bringing an example of these 16 diverse aldehydes. There are different ways to cluster them or to bring them into classes. And this is one of the issues that also the EPA right now are trying to do with the new chemicals categories. They're trying to make new categories, but categories cannot be statics. That it's a moving target. The more you add chemicals, the clusters will change, the categories will change. And it also depends on what are you trying to do with those categories. You don't have one specific goal. So to go back to QSARs, this is the diagram of QSARs. You start with the molecular structure and then its representation, and then you try to describe that representation. And it all happens in the feature selection. That's where the AI, the machine learning happens. And that's where you get to the activity. So I want to focus on those two things, the feature selection. That's what we're trying to understand here and link it to the key characteristics. And it's based on the descriptors. So what are the descriptors? And this is some work by Professor Tedeschini, who was my PhD supervisor. And he coded this software called Dragon for calculating molecular descriptors. And he brought this beautiful picture of a dragon from the Ishtar Gate. And it describes, it's a very nice metaphor to chemical structures, because the chemical structures, it's just a lot of different groups, right? Fragments. And each fragment can do something, but none of the fragments can work alone and do and cause the whole activity or toxicity by itself. It's a combination. But certain parts of the molecule are not always working for all the different endpoints that the chemical, or like the activities that the chemical is causing. So the way to describe the chemical is there are a lot of different steps and different information you can encode from the chemical structure. And here a presentation of how incremental is the information that you can extract from a chemical structure. It's not just the existence or the presence of a certain fragment or functional group that's going to cause toxicity. That's why a lot of people are not huge fans of tox alerts, because even if a chemical has a tox alert, doesn't mean it's going to cause a specific toxicity. And this is the reason. A chemical is a whole structure. It's not just one fragment, right? So that's why there are a lot of descriptors to describe. There are a lot of ways to describe a chemical structure. And the information varies, and the complexity of that information that can be extracted also varies. Here we bring like different levels from 0D to 4D. It can go from like something really simple, like the molecular formula, the molecular weight, the atom counts, and it goes up in complexity. You can bring like the different fingerprints, like the tox alerts or tox print chemotypes or things like that. And you go up in 2D and 3D descriptors. And there are over 5,000 or 6,000 descriptors right now. So the only problem with descriptors, and when you approach this issue of features in the chemical structures, is to try and link them directly. And this questions that always get asked about QSARs are like, what do these descriptors mean? And some try to bring a mechanistic interpretation by linking each one of the descriptors to the endpoint. But that's not the mechanistic interpretation, because it's not a one-to-one. And there are two big problems with that way of explaining or doing the mechanistic interpretation, is that certain descriptors can be correlated with the endpoint that you're trying to predict, but that doesn't mean it's the cause. And there are a lot of examples of by chance correlation. The other problem is that when you have, like, sometimes you have your endpoint and a matrix, and like you're sure that all the features, like all the parameters are there, but there is no correlation at all. And you're wondering what's going on, what's happening. And that's the problem with the univariate analysis. You cannot link one, it's not a one by one. Like you have your correlation, or you draw your heat map correlation matrix, and you don't see anything. And it's a combination of different factors. So it's not a unique factor that's gonna cause an endpoint or specific toxicity, is the combination. So how do we get to the right combination of those key features that cause a specific or key characteristic? It's using the machine learning. And this is how we can use the machine learning approaches to draw and get the right combination of the key features that are the most important. It doesn't mean that it's the unique combination. It doesn't mean it's the perfect combination. It just means it's a combination that works. That's all you need. So we also have, once you get that definition of the similarity, that it's specific to your endpoint or toxicity that you're trying to understand, we have to pay attention to the structure activity landscape, which is going back to the initial congenercy principle. I said it's based on the assumption that similar compounds have similar activity. Well, it's not always the case, or at least the similarity is very hard to define to a point that it's a smooth landscape. It's always a rugged landscape. And there are these activity cliffs and structural cliffs that we have to pay attention to. It's when two chemicals are so similar, but they're so different in bioactivity or toxicity, and vice versa. Two chemicals have the exact same activity, but so different. and that's the structural cliffs. So, and these are just some examples of these issues with the activity cliffs. So all these three chemicals are so similar. So they have the same shape, the same size, the same functional groups more or less, but they are so different in activity. Only one functional group is different here, and it's causing all the difference in activity. Machine learning algorithms can help you identify what's going on, what are the most important features here, and it can bring you the top highest compounds that are the most likely to have that specific activity, and then rank them. And then if these three chemicals are in the training set of the model will put the highest weight on that specific fragment, and it will put it in the top of the list. And that's how you know which are the key features that you're trying to look for. And this is another example just to show how the key features in a like when you do docking in the pocket, the ligand and the pocket and the interactions. So all these three chemicals here are also so similar. They have the same shape, same size, more or less, same functional groups, but they differ just a tiny bit to make the whole difference. And that difference is how to define a similarity for this specific endpoint and for that specific binding pocket. So the take-home message here is that there's so many ways that we can use the machine learning algorithms. They're all useful, but it really depends on what's the goal that you're trying to do. Most of the times they're used just to make a prediction. You have a chemical structure, you have a model, and you want to get a prediction based on that specific model. So you use the most accurate model, and you don't really care what's like. You use it as a black box, but it's not always like that. And for example, neural networks, they're the least interpretable algorithms. They're not very useful here. That's why in examples like this, I would suggest like something like KNN or like decision trees or things like that where you can interpret and link the key features to that specific endpoint. And that's how we get to a point where we link the key features to the key characteristics. Thank you.